Hello, everyone. This video is to illustrate the plane assumption in solid mechanics. So in solid mechanics, we use a plane assumption a couple of times. So the first one is when we talk about the shaft rotation, right? So if you twist the shaft, apply a torque, so the shaft will rotate. You can see here, right? So when you rotate, and now if I draw a line representing the cross section, so you can see this line, when I rotate it, it remains flat, right? So either way I rotate it, it remains as a flat. So based on this observation, we come up with the assumption of plane assumption, right? So that's for the deformation of the shaft under torsion. Okay, so this is one line. I can actually also draw multiple lines as shown here. So you can see if I rotate it, right? So you can see the this line, they're moving up and down, right? So rotated, right, a little bit, but they remain as a flat, here, right? So the cross-sectional planes remain flat when you rotate it, right? However, if you look at this longitudinal line, they actually rotate there. Okay, so if let's say we focus on one square here, right, the square here, right? So when you twist it, so you can see the square now get twisted a little bit, right? So it's actually shared a little bit, right? So deform a little bit. So we will base on actually this plane assumption to look at this deformation and then figure out the strain and the stress later on, right? So the same plane assumption, actually we can illustrate, for example, with this slink, right? So imagine this all these planes here, right? You have all this ring, each representing a plane. So when you apply a torque, you have a rotation, right? So you can see this figure here, right, get twisted. So you can see it get twisted, right? But all this plane, they remain as a plane. They just move, rotate relative to each other, right? And so the size of the shape, they remain the same. They just rotate, right? Or you can illustrate, say here, have a bigger one, right? So you can see this, they will rotate, right? You can see more clearly. They just rotate relatively against each other, right? So, but not really change its shape. It's remain flat, right? So this, I think you can see it's moving here, right? Okay, so this the plane assumption for torsion, right? Then in bending, when we have a beam, if we actually bending a beam, now we can also draw the line representing the cross-sectional plane. So that plane, actually, you pay attention, when I rotate it, it actually also remain as a plane when bending, okay? So you can see here, when bending, right? So the plane, that's all remain, they just flick, right, a little bit relative to each other, right? So you can see they move, right? So actually you see here, right, in the bottom, they get closer to each other, and the top, they get stretched, so that you can see the deformation is not uniform, right? And if we draw a line in the middle, like show here, right? So you bend it, so the bottom get closer, the top gets away, right? So this kind of under tension here and the compression here. So by reasoning, you can see here's tension, here's compression, this straight line, right? Straight plane. So there must be somewhere, right, in the middle, there is a, we call neutral axis. So this, at this point, the distance actually remain unchanged when you bend it. So that's the plane assumption for the bending. We're going to use that, derive the deformation, the strain and the stress in the beam bending situation, right? So we need this plane assumption to derive the deformation in the stress, because actually we see it's not uniform, right? On the cross section, right, the deformation is not uniform, right? So in the a bar, when you stretch it, right, and actually in that case, the strain you can see here, right? So this is like a bar, right? You stretch it, so you can see the cross-sectional plane. They are right, kind of stretched apart, right? So the distance between them is a little bit bigger, right? So that means elongation. But you can see it's remain straight, the lines, right? So that representing the cross section remain as a plane, right? But the difference is here, right? When you stretch it, because of Poisson's effect, so the lateral cross section, it gets smaller, right? So this side lengths get smaller. So it's actually the plane remain as a plane, but they actually shrink a little bit. So this is different from torsion twist and also from the bending situation, right? In this stretch situation, we didn't bring up the plane assumption because we really didn't need it, right? We know the stress is actually uniform in this cross section, right? So we can basically just the force divide by this cross-sectional area that give us a stress, right? It's uniform everywhere. So we just divide the area, get the stress. It's the average, but it also locally everywhere is the same. So that's the stress. Okay. So briefly, right? So the plane assumption is true for bending, right? And also for twist. All right. Okay. So that's kind of explain the plane assumption. All right. Thank you.